Today. I just switched. I don't know what you Okay. There you go. Just show up. Next week is the last day for lab. Like Chester, it's my last lab.
I totally got that.
Next week. Oh, yeah. Oh, I'm looking forward to it. And I can see by the way this week is ending, next week should shape up great.
You're funny.
Because the past always dictates the future. So the present right now will be the past next week. The future isn't looking right. All right.
Thank you. It's actually getting a lot better. I'm only one my
All right.
notes behind
What we're going to do today is finish up the respiratory system.
Thank you.
All right. We have started to introduce basically how we are able to transport oxygen and carbon dioxide once it gets into the blood. Okay? This is the transport of the respiratory gases. How they move in and out of the tissues or lungs, that's gas exchange, that's respiration. Right now we're looking at how we get them to and from those areas. In the case of oxygen, okay, or I guess I should backtrack a little bit. What determines how we are able to transport to a large degree is determined by how soluble the gas is in blood. Another way of looking at it is, since blood is 92% water, the liquid component anyway, how soluble is the gas in water? In the case of oxygen, oxygen is not very soluble in water. Just take a little furry thing and hold it underwater, or I'm sure you can go on YouTube, there's a couple of rabbits no longer around. And the lady from the pet store who held them under the water, and then their ears drooped. Oxygen's not very soluble. So in order for us to transport it in the high enough quantities that we need to sustain our metabolism, we have to have something in there that once it gets in, it can hold on to it, and that's hemoglobin. Okay? So when oxygen is forced into the blood, the red blood cells have a very high affinity because of the hemoglobin. So when oxygen gets in there, it binds to the iron, and then you form oxyhemoglobin. And then that is how we transport it. We do dissolve a small amount of oxygen into the plasma itself, but it's, like around 1%. So 98 to 92% of the oxygen we carry through the blood is by way of hemoglobin. Carbon dioxide, by comparison, actually gets carried 3 ways simultaneously. So this is a little bit more involved. It still depends on the solubility, but there's a little bit more chemical stuff going on with the carbon dioxide. So the 3 mechanisms, the 3 ways we transport carbon dioxide, so we'll just call this CO2 transport. Way number 1 is by attaching it to hemoglobin. All right, we call the carbon dioxide, it doesn't compete with oxygen. Oxygen attaches to the iron on the hemoglobin. What carbon dioxide attaches to are the amino acids on the hemoglobin. So it forms what is called carb for carbon dioxide, amino, saying that's attached to the amino acids in the protein chains, carbaminohemoglobin. A second way we transport carbon dioxide is directly in the plasma. It will attach to chemicals and stuff, or dissolve right into the water in the plasma. The third, and this is the main way, this is the primary way that we transport carbon dioxide, is we will take the carbon dioxide and convert it to another chemical. So there's a chemical reaction here, and that chemical is HCO3 with a minus sign, and that's called bicarbonate ion. So what we do is we, through chemical reactions, convert carbon dioxide to bicarbonate ions. Just to give some relative numbers to this, and I know, I'll just put the numbers here. Of all the carbon dioxide we produce, about 70 to 80% gets converted to bicarbonate ion. Carbaminohemoglobin is going to be about 10 to 15% of all the CO2 we produce. That's how we're going to carry it there. And somewhere approximately around 5%. Again, I'm just using kind of middle of the range numbers on here. Different authors will use different percentages, but the quantities don't change. This one's always the highest amount, this one's always the next highest, and this one's always the lowest. That's why I just put these here to give you a kind of a relative perspective. All right? So most of the carbon dioxide we convert to bicarbonate ion. And for a large degree, that's why our blood is 7.35 to 7.45, because bicarbonate ion acts as a base. It's a weak base, but we use that to help neutralize other acids and stuff like that. And then we carry with the carbaminohemoglobin and then directly into the plasma. Now, how do we go from carbon dioxide to bicarbonate ion? That's a chemical reaction. Basically what we do is we start off with carbon dioxide, and the other major component of plasma, which is water. So what will happen is, over time in the plasma, the carbon dioxide basically gets hydrated. We attach water to it. So that occurs within the plasma, but very, very slowly. That's why most of it, in that case, carbon dioxide dissolves in there. What we will do is get carbon dioxide into the red blood cell, where there is also water, and once it gets into the red blood cell, we add an enzyme to this called carbonic anhydrase. Carbonic anhydrase. This is an enzyme. This is found in the red blood. It's found in a lot of tissues, but At this point, it's found primarily in the red blood cell. Since it's an enzyme, it carries out a catalytic reaction. It catalyzes the binding of carbon dioxide and water. They don't normally want to do it under our normal body temperature. They can do it under other conditions, but not normally our physiological conditions, and that's why we have an enzyme. The enzyme makes it occur within our body. So what happens is the carbon dioxide and the water combine, and that gives us a chemical called carbonic acid. All right, so the number of atoms and everything we start with is the number that we have to end with. So we start off here, we have 2 hydrogens, so I'll just put those over here. I look in here between the carbon dioxide and the water, I have 1 carbon, so I'll put that right here. So I took care of the hydrogens, took care of the carbon, and now I have how many oxygens? 3. When we do that, we form this chemical. This is called carbonic acid. We're still not at bicarb yet. So what we have to do now is knock off one of the hydrogens. Notice the formula for bicarb has 1 hydrogen, 1 carbon, 3 oxygens. Carbonic acid has 2 hydrogens. So what this has to do is ionize. Since it's an acid and it's in water, that's what it does. It ionizes, so it knocks off one of the hydrogens. So that's an H+, and then we are left with HCO3-. Here is our bicarbonate ion. Once the bicarbonate ion is produced, this is primarily in the red blood cell, the red blood cell will push it out into the bloodstream, into the plasma. It pulls in chlorine. That's called the chloride shift. You don't need to know it, but they make a big deal about it. And then now the bicarb is out in the plasma. So what we have done, we have taken a waste product that is formed from what reaction? Cellular respiration. We have taken a waste product that we're ultimately going to eventually get rid of, but through this chemical reaction, we now convert it into bicarbonate ion, which we use now to help maintain the pH of the blood. So we've taken a waste product and converted it into something useful. That's green. For you kooks that hug the trees. That's green. Before we get rid of it, and it causes global warming, we use it to control our pH of our blood. Yeah, all that warmth for that. All right? So that's how we transport this. Now, this is going from my picture here. This is the tissue. Let's say this is the muscle tissue, and this is the bloodstream going through. All right, so this is how we get the carbon dioxide to go. Once we get to the lungs, we just kind of reverse this process. We'll take the bicarbonate ion, backtrack it to carbonic acid, and then basically break it down again into carbon dioxide and water, and then that's what we exhale. So before we exhale it, it actually goes through a whole series of chemical reactions and steps. So number one, we can transport it. And number two, the result of those chemical reactions gives us chemicals that we can use for other things in the body. And one of them is to maintain pH. So this goes back to one of the first functions that I listed on the respiratory system. One of them is gas exchange, and the other one, a very close second, is to help maintain pH, especially of the blood, maintaining one of the properties of blood. Yeah,
Now, if the body's using the bicarbonate ions, they're using some of those up to maintain pH. What happens to all the hydrogen ions? What does the body do with those?
the hydrogen ions, couple of things. They will attach to proteins either in the red blood cell or the plasma, so they will act as a buffer. Or they'll attach to the hemoglobin. So, without getting into too much detail, the proteins form what is called the protein buffer system. So what they do is any loose hydrogens, they will absorb them. As long as a
So
hydrogen ion...
it wouldn't be like a toxic waste product. It'll be used somewhere by the body.
Yeah, exactly, exactly. The proteins will attach it. As long as hydrogen is attached to something, it's not acidic. It's when it's floating around unattached, H+ form, that's when it's going to be a problem. So as long as we attach some to the hemoglobin, you can see it here. After the hydrogen's made, we will attach some to the hemoglobin. So that has a normal buffering system. And in fact, we need that, as you'll see in a little bit, to knock oxygen out of the red blood cell. Or we will attach it to some other protein. So those two things are the protein buffer system and the hemoglobin buffer system. So nature's got it figured out. Figured out that, yeah, okay, we form this chemical, but I also have to deal with this, so that's how we do it. And then eventually, by keeping these things in normal quantities, that means we don't produce too much hydrogen atoms or hydrogen ions, thus we don't become too acidic. How we balance that out is through our ventilation. That's how we balance it out. So when we need to increase carbon dioxide removal because potentially we're producing too much acid, we will then increase respirations. There's an area in the brain, it's called the chemosensitive area, and this is constantly monitoring the hydrogen and the carbon dioxide. If both of those get too high, that means, or the area in the brain assumes you're becoming too acidic. Because if you retain carbon dioxide, you're going to produce more carbonic acid, thus more hydrogen. So then your respirations will increase. So when you see anybody going into a condition called acidosis, metabolic acidosis, and this is one reason why you take respiratory counts on patients every day, changes in their respiration could indicate changes in their acid or base levels inside their body. So if I had a diabetic, and all of a sudden for a couple of days respirations are fine, and then I see them increase, it could mean that they're going into ketoacidosis, or they might have an infection. Infections generate a lot of acidic waste products that will get into the blood, and that will increase their respiration. So now you start looking for problems. Even before they're visible, you might be able to do a simple blood test or a culture and get something very early before it manifests into something drastic.
In the chloride shift, are you saying that it's the bicarbonate ion that gets pushed out?
Yeah,
Does that just happen like whenever it gets to the lungs?
and it happens in the bloodstream. It's happening all the time, not just in the lungs.
So then does,
What it's doing is, it's exchanging a negative charged chemical for another one, because the interior of the cell has to have a certain electrical balance. So if you take something with a negative charge and pump it out and don't replace it, the interior of the cell will become too positive.
so does that carbon then never get taken to the lungs? From the,
You mean the bicarbonate?
yeah.
Yeah, when we get to the lung, because this is eventually all gonna go to the lungs at some point.
So does it go into the plasma, is that what you're saying?
Yeah, what'll happen is, when it gets to the lungs, they'll just reverse that. Okay, the chloride will get pumped out, which will allow the bicarb to come in. We reverse, and then we breathe out the carbon dioxide. If you don't have enough chlorine in your blood, you won't breathe out enough carbon dioxide. That's why you have to have that. Yeah, but salt's bad, Dr. Ryan. I saw that with the Dr. Oz show. He said it's bad. Yeah?
He's a kook.
Go into hypochloremia. See what happens. Nothing is bad, nothing is good. It's too much or too little that is bad or good. Not good. All right, but in order for this to balance out, you do have to have a certain amount of chlorine. So people that vomit a lot, they will lose large amounts of chlorine because that chlorine then gets used by the cells in the stomach to produce hydrochloric acid. So if you're vomiting a whole lot, it's going to affect your respirations because you're disrupting one of the chemicals you need for gas exchange to occur, and that's the chlorine. You don't think about it, but it's needed to occur. Everything has to be balanced out here. Okay? Any questions on this? All right, so now we see how we can transport the oxygen and the carbon dioxide through the blood. Now, if we shift back to oxygen, oxygen is the primary chemical through all of this. Because ultimately it is being able to get oxygen into the blood that we can get it to the tissues, as we can see here. Goes from the blood into the tissues, so that way they can use it to produce ATP. But now we have to introduce another set of circumstances on how do we get oxygen to go from the blood into the tissues. At this point, we just say, well, oxygen goes in. You know? But in order to go from the blood into the tissues, there are certain things that have to occur. All right, now, most of the oxygen, as we said, is going to be attached to the hemoglobin. So HB means hemoglobin. This rectangle here is going to represent a chemical bond. And then attached to the other end of that bond is going to be oxygen. So when oxygen binds to hemoglobin, it forms a chemical bond. This is a type of covalent bond. It's called a coordinate bond. And it's unique. It's unique. It has to be strong enough to hold the oxygen, but it has to be weak enough to break very easily to allow the oxygen to go. As long as oxygen is attached to hemoglobin, it will never leave the cell and go into the tissues. Never will. All we want the hemoglobin to act as is a taxi. Drive it to the cell, and then allow the bond to break. Oxygen leaves the taxi and then goes into where it has to go and be utilized. Okay? So in order for that to occur, chemical reactions have to take place, which is fine. This process is called oxygen unloading. You will also see the term oxygen dissociation. That's the technical term for it, but quite often you can say, well, they got to unload the oxygen. Now, we do not give off all the oxygen that our blood is carrying, okay? Let's say we have arteries then we have a network of capillaries, and then we have veins. And some people measured this, okay? The average concentration amount of oxygen going into all of our capillaries all at the same time, okay, is going to be about 20 milliliters of oxygen entering into all of our capillaries every second. While in the capillaries, the oxygen that's in here, we have to let that oxygen leave to feed the tissues. Someone said, well, how much oxygen is in the blood that's draining the capillaries? So we're sending 20 milliliters of oxygen, which is a lot, to the capillaries. How much is in the blood leaving the capillaries? So you're going to see it drops down to about 14 milliliters, 14.5. So we sent 20, but under ideal situations, we were only able to extract somewhere between 5 and 6 milliliters. So only about 20 to 25% of any amount of oxygen that's sent through the bloodstream gets pulled out at any one time. So that means we have to constantly recirculate. Does that make sense? It might go up a little if these cells are active, go down a little if they're resting, but that's going to be about an average. So someone said, well, what's maximizing, what's making it so we are only getting rid of, we send a lot, but we only take out a relatively, I guess it's about 1/5 to 1/4 of the oxygen that's sent there is actually going into the tissues. And they figured out it's this bond. It's not just simple going in and diffusing out, it has to break that bond. So that means there's other chemicals involved in the dissociation process. So what are some of those chemicals? One of the chemicals that is needed to break that bond to release the oxygen so it'll go into the tissues is hydrogen. Hydrogen, when it is formed from a bicarbonate ion, will attach to the hemoglobin, and what it does, it causes this bond to break, or a certain amount of the bonds to break, which will then allow oxygen into the tissues.
I hear you that. What causes the bond to break?
Hydrogen.
Hydrogen.
It attaches to the bicarbonate?
No, it's from the
From the
bicarbonate.
bicarbonate.
The hydrogen comes from the bicarbonate. It's floating around. It then attaches to the hemoglobin. Once the hydrogen attaches to the hemoglobin, it will break that bond that's holding the oxygen to the hemoglobin. Once that bond is broken, it's like cutting the string on a helium balloon. Woo! Now it goes. So hydrogen ions. And anything else that increases hydrogen ions will break that bond. So generally, anything that causes your body to become acidic is going to cause your oxygen to dissociate or leave the hemoglobin into the tissue. So what is the name of that acid that you produce when you are exercising?
Lactic acid.
Lactic acid. That diffuses into the blood. The lactic acid with its hydrogen ions gets into the red blood cell, and it will cause more oxygen to go from the red blood cell into your working tissues. Now then, the trade-off is the more oxygen you use, the more carbon dioxide you're going to produce as a waste product. So it kind of feeds on itself. Okay, we call this effect of hydrogen ions causing oxygen to be released. This is called the Bohr effect. Bohr effect is when you increase hydrogen or you decrease pH. They're the same thing. If you increase oxygen numbers, you lower the pH, become more acidic. So when you increase hydrogen or decrease pH, it causes more oxygen to leave the tissues. So it increases oxygen dissociation.
What was that, Larry? What was the last thing you said?
It increases oxygen dissociation. That's what all this is for. How am I going to get that oxygen to dissociate? Leave the hemoglobin. I don't want to be associated with it. I'm going to dissociate myself from it. How am I going to get that to occur? One way to do that is through the acids. Okay? If you increase body temperature, an increase in body temperature will cause that bond to become more brittle and break easier. So the higher the temperature is in the tissue, the easier it is for the oxygen in the hemoglobin going through that tissue to leave the red blood cell. So what do they tell athletes to do before they go out and perform?
Warm up.
Warm up. That car before the game won't do a frickin' thing. It would actually have to be a couple of days. You'd be better off drinking water. So by warming up the tissues ahead of time, that will increase the oxygen uptake by those tissues. And again, that's why they tell athletes to warm up, because their performance is going to depend, let's say, on how well the muscles contract. And how well they contract is going to be determined by how much ATP they can produce. So if you warm up the tissues before you need them to use the oxygen to produce ATP, you're putting them in a better physiological condition to extract the oxygen directly out of the blood at a faster rate. Does that make sense? So an increase in temperature will do it as well. And the longer it takes for that temperature to reach the perfect temperature, the longer you're going to have to warm up. So a day like today, if you were to have to go out and run a marathon, it might take you a little bit longer to reach your normal training level speed or pace than it would be if it was something, if it was 75 degrees or something else. That's why they always tell you, if it's cold out, take a little bit longer to warm up. Less chance of injury. Okay? Any questions? Now, when you go into fight or flight, do you need more oxygen in your muscles and everything?
Yes.
Yeah. Yep. You don't have time when you're in fight or flight to worry about, whoa, Mr. Grizzly, I gotta warm up here. Just give me a few minutes. This thing is... You don't have that, do you? Now, that would be pretty funny. That's not what's going to happen. So what we want to do is we want to have hormones or chemicals that can very quickly break that bond to get more oxygen into the muscles because I have to go from doing nothing to running as fast as I can to save my freaking life. Or for being as strong as possible to throw the person next to me to the freaking bear. Use the buddy system. Give me your buddy. Okay? So there is a chemical that is produced. It is called BPG. Biphospho P glycerate G. Biphosphoglycerate. This is a chemical produced in the red blood cell, and what that will do, it will cause more oxygen to break from the hemoglobin and go into the tissues. It will increase oxygen dissociation.
Wait, you said causes more oxygen to break what?
Break free from the hemoglobin. You guys don't got that dissociation thing then, do you?
No.
Yeah, oh, I can see that. When you associate with somebody, what do? Associate with them.
Communicate knowledge.
Yeah, you're working with them. You're near them. When you dissociate, yeah, you need to dissociate from that boy. Bad news. You want to put distance between you and them. So, in dissociation, the oxygen wants to put distance between it and the hemoglobin. It does not want to be attached to the hemoglobin anymore.
Where did you say the BPG is?
Red blood cells. They make it.
Can you give us an idea of what the question on the test about this would?
Which of the following would increase oxygen dissociation? Which of the following situations would decrease? What? Yeah, go ahead. If the hemoglobin is just a car, it's a taxi. Do we know what that is, a taxi? Okay. You get in the taxi. Now, for a period of time, you're associated with that taxi because it's carrying you around. But then you want to get to the hotel because you want to get to the bar. But the taxi cab driver welds the door shut. You now no longer can dissociate yourself. You can't leave. So hydrogen's going to have to come by, break that weld, open those doors and say, leave! So now you are dissociating yourself from the taxi that was just driving you around. Exactly. Does that make sense? If hemoglobin is the taxi cab and the oxygen is you, all I want the hemoglobin to do is carry the oxygen to the tissues. Once it gets to the tissues, that oxygen has to break away from the hemoglobin because it's stuck to it by that bond. If you don't break that bond, oxygen will never leave. It'll just stay there and it'll just continue to go around.
So the iron helps us.
That's why the iron's there. Because without the iron, we don't carry enough oxygen in our blood. Well, the bond would be the seat belt. The iron would be the seat. Okay?
I'm screwed.
You still don't.
No.
You know why? Because I said it's chemistry. I'm done. I'm done. I'm done. I'm gonna fail. I'm gonna fail because he said chemistry. He said chemistry. He should have said like, this is easy. Those days are gone.
Mm-hmm.
Now, Anything that increases BPG production will also increase dissociation. It will cause oxygen to leave the red blood cell. Well, now this is where hormones come in. So for example, epinephrine will cause the red blood cell to increase BPG production during times of fight or flight. So the adrenaline gets into the blood, mixes with it. Obviously, since there's red blood cells in the blood, the epinephrine gets in, causes the red blood cell to produce BPG. BPG basically cuts through that bond and causes more oxygen to get into your tissues, primarily muscle, brain, and those. Heart pounding. So you can have plenty of oxygen in the blood, but if you don't have anything that can break that bond and trigger dissociation, you're not utilizing the oxygen as efficiently as you could. You're making ATP, but not as much as you could. All right, another hormone which works similar to epinephrine is thyroid hormone. That will increase BPG production, which will increase oxygen dissociation and ultimately lead to more ATP. Now, people that don't produce enough thyroid hormone, are they breathing? They get the oxygen into the blood, their volumes and everything are fine, but when they are hypothyroid, what's always their description of how they're feeling? I'm tired. How can you be tired? You're breathing, you got plenty of oxygen, you should be making ATP. I'm tired. Yell at me, it's not my fault. Ronnie Deutsch, she told me it's not my fault. They've got plenty of oxygen in the blood because they're taking deep breaths. But what are they not doing? They're not, what? They're not breaking that bond, they're not dissociating. Because without enough thyroid hormone, more oxygen stays in your red blood cell than goes in your tissues. So that's why they're always tired. Make sense? And without the ATP, you can't generate heat. So now their body temperature is low in their tissue, and that just kind of feeds on itself. So they're by losing out on this one thing, they're affecting the other things as well. Because they can't generate enough body heat. I'm always cold. I hate that. My fingers are freaking cold. All right? So these two hormones will do this. Now, other things we have, although not a hormone, cocaine will do it. Oh, yep. Cocaine will do it. That's one reason why you can maintain an elevated metabolism. And then it also causes an increase in thyroid hormone and epinephrine, so that's why you get the effects of that. You get the coke into you. You're hanging out down in Peru. Yeah, the Indians down in Peru by the, what was it, the Andes, at those high altitudes. At high altitudes, there's less oxygen in the air. So any oxygen you get into your blood, you want to hold on to it longer to deliver it, and then, so that's what cocaine does. That's why it's grown in high altitudes. So those people are constantly munching on it, like chewing tobacco. Believe me. You get the process. Okay? Caffeine will do it. So notice any stimulant will increase BPG, which will then cause more oxygen to unload or dissociate from the red blood cell, and then we can produce more ATP. Make sense? Okay? So it's not just enough to get it into the blood and then have the blood carry it, although that's important because that occurs before dissociation. But once you get the red blood cell to the neuron or to the muscle cell, we now have to have the oxygen leave or dissociate so it can go out of the red blood cell and into that particular tissue, and then the tissue can use it for ATP production. Does that make sense? Has to have it go in that fashion. Okay? All right. Any questions on that? All right. Now, the next thing we want to take a look at is how do we match, and clinically this winds up being important. We have to, and the body's constantly adjusting this, we have to basically coordinate three basic things in order for this to occur efficiently. We have to coordinate ventilation, so we have to coordinate the amount of air we breathe in and out. We have to coordinate that to the amount of blood that we send to the lungs. So that's pulmonary perfusion. And then we have to coordinate that with blood flow to the tissues. So we have to coordinate breathing, blood flow to the lungs, and then we have to coordinate those two things with circulation to the tissues. Any disruption in that coordination, the bottom line is you're not going to be able to send enough oxygen to the tissues. So when we take a look at the coordination between breathing and blood flow to the lungs, that's called ventilation perfusion coupling. Oh my God, another coupling!
Wait, will you repeat that?
Ventilation perfusion coupling. This is how we coordinate breathing with blood flow from the heart going to the lungs. And if you can't do this very well, they are going to send you someplace and they will perform a scan. You'll have to breathe in this glowing air. It's called a VQ scan. Has anyone ever had to have those? Ventilation perfusion scans.
It sounds familiar.
Ventilation perfusion scans, they'll do that if someone's not oxygenating their blood, but it looks like they're breathing. So let's say they have a pulmonary embolism. You will send them to see what's their VQ scan. Because they're getting enough air into the lungs, they're just not sending enough blood to the lungs to pick up the oxygen. So clinically, you're always adjusting this. You're looking for this. Okay? Or if you block your airway, your heart's sending enough blood, but are you getting enough oxygen in to the blood? No. If I just do one test, I'm going to get the same result. Not enough oxygen in the blood. I now have to assess why. Are you not breathing enough oxygen in, or are you not sending enough blood to the lungs? I have to couple them. Ventilation perfusion. Okay? We're always constantly adjusting them. So anything that would decrease blood flow to the lungs, we generally compensate by taking deeper breaths to try and increase the amount of oxygen availability. Anything that would send too much blood to the lungs, we will generally decrease our breathing, at least for a period of time. So you would see this in somebody with congestive heart failure, because their lungs are filling up with so much fluid that they're starting to spill in. So what they're trying to do is decrease some of the breathing that's getting there, because then that's going to increase carbon dioxide and stuff like that. So we're constantly adjusting that. Now, how do we compensate for these changes? Well, the nervous system basically has to call the shots here, because the nervous system is constantly monitoring lung function and cardiac function, as well as blood flow function through the body. So the nervous system is constantly basically at the control panel trying to coordinate these things, so that way we do three things. We maintain CO2 levels, we maintain oxygen levels, and we maintain pH. So the nervous system has to control the ventilation perfusion coupling to make sure that we always have enough oxygen, not too much carbon dioxide, and our pH stays between 7.35 and 7.45. Because any alteration of one will knock the others out of sync. So now we're taking a look at the neurological control of breathing. That's where most of the, well, we're in the respiratory chapter, so that's where we're. Well, in general, here's how we, you don't need to know this, this kind of goes into a little bit more detail than I normally do. But what this is doing is it's showing us how if you reduce your breathing, you reduce ventilation, okay, you are going to shift or alter your blood flow to the lungs so they always match up. If you decrease blood flow, you're going to change your respirations, your ventilation, so they always match up. How that occurs, we don't need to do it. But the bottom line is, the reason why we breathe at the particular rhythm and rate is also synced up to the cardiac output and the amount of blood going to the lungs. We often don't think about it, but there are. They call it a ventilation perfusion ratio. We ventilate a certain amount of gases, we breathe in and out, to match a certain amount of blood flow to the lung. All right, neurological control of breathing. For a long time, people looked for, they were ripping lungs out of people, cutting them up, slicing them up, and looking through them, and they were looking for like a pacemaker. Heart has a pacemaker, so they thought the lungs did. So the lungs have no intrinsic capacity to increase or decrease their ability to respirate, to expand and contract. So it is completely controlled by the nervous system. Since it's the nervous system, do we have to think about increasing or decreasing our heart rate or breathing rate most of the time? No, it just seems to occur. Just seems to occur. So generally there are reflexes, circuits in place that are either monitoring stimuli or changes that will lead to a change in the breathing pattern. We have receptors in the brain, and we have receptors in certain areas of the vascular system that are monitoring basically three things. They're monitoring oxygen levels, carbon dioxide levels, and associated with pH to measuring hydrogen levels. The one that has the biggest influence on your breathing rate is hydrogen. Believe it or not. The one that has the least amount of influence on your breathing rate is oxygen. Oxygen levels can drop pretty drastically before you change your breathing. It's the biggest thing that adjusts your breathing are these slight changes in pH in your blood. Question? So we have an area in the brain, it's called the chemosensitive area. This is in the medulla. And what's chemo mean? What? Chemical. Chemical. The chemical that this is monitoring is basically hydrogen ion. So when hydrogen ions increase in the blood or cerebrospinal fluid, and it would usually occur in the blood first and then the cerebrospinal fluid, that will activate the chemosensitive area, which will then send impulses down, basically getting to the phrenic nerve to go to the diaphragm and increase your respirations. So when your body becomes too acidic, we increase our respirations. And the classic example is somebody who's going into ketoacidosis, a diabetic. By increasing ventilation, by increasing the respiratory rate, we can try and compensate for the changes in pH by getting rid of carbon dioxide. If you increase CO2 removal from the body, this will increase blood pH. If you retain carbon dioxide, that will decrease blood pH. So if we increase CO2 removal by going into hyperventilation, the acidic changes in the blood will then start to reverse, and we're going to make them come up more to 7.4. Does that make sense? If we become too alkaline, this would be if we become too acidic. If we become too alkaline, we want to keep carbon dioxide, so we decrease removal of CO2. So we decrease respirations, which will cause the pH of the fluids to drop. So notice, if we're too basic, we try to become more acidic. If we're too acidic, we try to become more basic. Basic reflux. And this is the area of the brain, the chemosensitive area. This is what it's trying to do. It's constantly trying to adjust respirations, ventilation to your pH, one of the factors that will affect it. It's always trying to do it. So anything that would cause your body to become too acidic, certain medications, overdoses, or anything like that, one way that the body's going to try and compensate is through ventilation. All right? Any questions on that? Now, to adjust the normal ventilation rate, okay, this is the area that kind of is constantly monitoring the chemical components that we need to adjust to. But there are those times where we just have to increase or decrease our ventilation for other reasons. So we have other areas of the brain for that. In the medulla, we have a region called the medullary rhythmicity center. Medullary rhythmicity center. We learned about this in the brain. The medullary rhythmicity center, okay, is in the, obviously according to its name, the medulla. And this is the area that helps to adjust the normal rhythmical pattern of breathing. The inhalation and the exhalation. We have the medullary rhythmicity center. This is adjusting the normal rhythmical pattern of breathing. Now, in order for that to occur, this area in the medulla has to talk or work with an area in the pons. Actually, two areas in the pons. In the pons, that part of the brain stem, we have two primary areas. One is called the apneustic area, and the other one is called the pneumotaxic area. The apneustic area in the pons, what the neurons in this area, and these are nuclei. What's the definition of a nucleus? A group of neuronal cell bodies in the central nervous system. So the neuronal cell bodies in the apneustic area, they want to trigger inhalation. They want to trigger inhalation. The pneumotaxic says, screw you. I have to listen to you. I trigger exhalation. So now they're like two kids fighting. Mine, no, I go, no, then. So now somebody has to come in and coordinate them. It says, look, I'll let you do your thing for a period of time. And then when I say stop, you got to stop. And then I'll let them do their thing for a period of time. And I'm going to tell you the same thing. When I say stop, you got to stop. And that's what the medullary rhythmicity center does. It coordinates the activity between the apneustic and the pneumotaxic. So when we inhale, the pneumotaxic area is turned off, and the apneustic area is active. So the medullary rhythmicity area is looking at the apneustic area and it's going to say, I'm going to allow you to go to inhale for about 3 seconds, 2 to 3 seconds. And then after that time, the medullary rhythmicity area turns off the apneustic and says, you had your fun, now the pneumotaxic center could go. Now you exhale, generally for another 2 or 3 seconds. And then the medullary rhythmicity center says, okay, pneumotaxic, you did yours. Now you stop, and that apneustic kicks in. Now you start to inhale for another 2 or 3 seconds. And then it triggers pneumotaxic to kick in for another 2 or 3 seconds. So So notice the medullary rhythmicity center is not triggering inhalation or exhalation, at least directly. It's turning on and off the areas that do directly.
So what happens whenever you get the wind like that, you go into the exit?
Well, part of that's the air pressure is, so now you gotta wait for that pressure to equalize. Okay? Now, if something happens to the brainstem, you're gonna lose this coordination. And what other area is also in the brainstem that works with the heart? No. Works. Okay, I'll take it. It's in the medulla. Cardiovascular center. So we've got all of this neuronal activity coordinating breathing with cardiovascular changes all at the same time. This is why if you have brainstem injury, you're probably going to die. Okay? So the medullary rhythmicity center just controls the rhythmical pattern, the inhalation and the timing of it, and then the exhalation and the timing of it, and not just the length of time you're inhaling or exhaling, but that length of time when you immediately end inhalation, there's a pause, and then you start exhalation. It's controlling that in-between time as well. It's controlling all aspects of the rhythm, the inhalation, exhalation. You can tell when someone's center ears are not working, they have a very disrupted too long of a pause between inhalation and exhalation.
So, the kid trying to keep up.
Well, when someone cries, that's got to get coordinated because it's going to change your breathing. So the brain has to coordinate emotional aspects to the changes in breathing to still maintain oxygen levels, CO2 levels, and pH levels. Brain has to coordinate all of that. Every time we talk, it has to take into account all of this because that's going to slow down the normal just breathing. It takes longer to exhale when you talk than it would be if you were not talking. So the brain has to coordinate it because that means you're holding on to carbon dioxide more. That means there's less oxygen getting into the system within that same time frame. Does that make sense? So it's not just as simple as oxygen in, oxygen out. There's a lot of coordination to make sure the fact that we do these things every day, they don't potentially harm us or disrupt our physiology. Okay? Now, we do have some protective reflexes. We do have what is called a stretch reflex in the lungs. A little bit different than those type of reflexes we looked at in skeletal muscles. What this stretch reflex does, it prevents overexpansion of the lungs. Because if you overexpand the lungs, let's say you hook them up to a ventilator. And you say, they're hooked up, let's go to lunch. But they're taking more air in. So what are we going to ask those lungs to do? Expand and expand and expand. And potentially, without this protective reflex, they would rupture. Or at least get damaged. So we have a stretch reflex. There are stretch receptors within the bronchi and the lung tissue. So if the lung expands more than it would normally do, it will trigger this reflex to trigger an exhalation. So that way, whatever force is causing it to want to inflate, the lungs are countering it reflexively to deflate. So it prevents lung damage. So you have to adjust these things if someone's on a ventilator. Now, it's hard to do that under normal circumstances. But on a ventilator, the mechanical pushing in of the air, that has to be adjusted, so you don't trigger that. It's called the Herring-Brewer reflex, it's a stretch reflex. So you don't trigger that, because then they're just going to be exhaling. You're sending air in, but the body's fighting you in exhaling. So their amount of ventilation is not going to be very good. So now I'm going to disrupt that ventilation perfusion stuff. All of this neuronal coordination and everything has to be adjusted so we can maximize oxygen and carbon dioxide to do this. What is that?
Cellular respiration.
Cellular respiration. Because when you get into the chemistry of it, you can disrupt things if you send too much ingredient in to get utilized. Back up. So it's going to slow down ATP production. Too much going in can give you just as it can reduce ATP, just like not sending enough ingredients in. And if you retain too much waste product, it will slow down ATP production. So if you start to retain CO2, that can slow down ATP. But if you get rid of it too quickly, it's going to cause disruption. It's going to throw this out of balance. So we constantly are fighting through the adjustment of breathing, heart rate, and blood flow. Ventilation and perfusion means blood flow to the various areas to maximize ATP production. Always, always, always. Any questions?